So welcome everyone to another edition of the Symmetry Seminar. Today we have Yichul Choi with us from Stony Brook University, who will tell us about higher Berry phase of free Dirac Fermions. Please take it from here.
Okay, thank you, Laksha, for the introduction. And thanks everyone for coming. And I also want to thank the organizers for inviting me to give a talk at this nice seminar. So today I will tell you about higher Berry phase of free Dirac Fermions. And then the talk will be based on the work that I did with Kantaro Omori. And then the paper was put on archive a few weeks ago. So here is the outline of my talk. So I will begin by reviewing the notion of invertible field theories. And then I'll introduce a little bit more generalized notion of invertible field theory, which is called parameterized invertible field theory. And then I'll introduce what is called a higher Berry phase. And then I'll go to the main topic of this talk, which is the free Dirac Fermions with spacetime-dependent mass parameters. I will show you how to compute the higher Berry curvature for such a free Dirac Fermion systems in general case. And then I will show you a simple example of a non-trivial Berry phase with vanishing Berry curvature in the end, and then I will summarize. So as a disclaimer, I should say that in this talk, there will be no non-invertible symmetries at all. And also there will be no higher form symmetries almost at all as well. If anything, my talk will be related to something called minus form symmetries. I hope the talk is still enjoyable. Okay, let me start by reviewing the notion of invertible field theories. So by now it is well understood that the infrared limit of a trivially get QFT is described by an invertible field theory. So an invertible field theory is a particularly simple example of a QFT, and its defining property is that the Hilbert space on any spatial slice is simply a one-dimensional complex vector space. So this is an extremely simple type of a QFT, but still we are interested in studying them because of various reasons. So broadly speaking, there are three main reasons to study invertible field theories. So first of all, these theories are known to describe the so-called symmetry-protected topological phases of matter in the condensed matter physics literature. And secondly, they correspond to Hooft anomalies in one-lower dimensions via the anomaly inflow mechanism. And finally, the set of invertible field theories tells us what are the possible discrete torsion phases that one can put when you try to gauge various symmetries. So these are the main reasons to study invertible field theories, and is for me. And one important property of an invertible field theory is that an invertible field theory is completely characterized by its partition function on closed manifolds in the presence of various background fields. And this understanding of an invertible field theory enables us to completely classify the set of invertible field theories almost at the level of mathematical rigor. So by the work of these authors, by now it is well known that the set of invertible field theories in a given space-time dimension D with a given symmetry type is the set forms an abelian group. And this abelian group I will denote by this notation. And here this bullet point means that this denotes the tangential structure of your space-time manifold It could be oriented, unoriented, spin, etc. And this P is usually some kind of classifying space or some higher analog of the classifying space, which specifies the internal symmetry of the problem that you are interested in. And then the statement of the classification theorem is that this abelian group is identified with something called the Anderson dual of Bordism groups. And in turn, this Anderson dual of the Bordism group is isomorphic to this group that I wrote on the right-hand side. And at first sight, this may look complicated, but the important thing that I want to mention is that this decomposes into two abelian groups. So the first factor, the elements in this first set are so-called Bordism invariants. And then by the anomaly inflow mechanism, they correspond to non-perturbative anomalies in one-word dimensions. And then the elements of this second set can essentially be thought of as a degree d+1 differential form. And these are nothing but the anomaly polynomial for the perturbative anomalies in d-1 dimensions. And then what this classification theorem essentially says is just the previous statement that an invertible field theory is completely characterized by its partition function. So for instance, if I have an invertible field theory given by some Bordism invariant, then its partition function on some closed spacetime manifold is simply given by evaluating this Bordism invariant on the spacetime manifold, which will give me some phase vector. And on the other hand, if I have, say, some element from here, which I said can be thought of as a degree d+1 differential form, I write this differential form as bd+1. Then if I want to compute the partition function of a corresponding invertible theory living on a spacetime manifold XP, and what I need to do is to simply extend this manifold to higher dimensional manifold. And then the partition function of the invertible theory is simply given by integrating this anomaly polynomial along this higher dimensional part. And then because this anomaly polynomial is quantized, the partition function will not depend on the extension to the higher dimensional part. And more generally, if you have some pair of elements from this set that will define some invertible field theory, and again, there is some well-defined way to compute this partition function and vice versa, but I will not go into too much details. So please interrupt me at any point if there are any questions. Yeah. So all these things look very abstract and mathematically complicated. But simply put, all these mathematical statements just mean that an invertible field theory is essentially a classical counterterm or a classical effective action for various background fields. You obtain this effective action by integrating out trivially gapped dynamical degrees of freedom. And usually these background fields are background gauge field for the symmetries of the system that you are interested in. So for instance, if you have a zero form internal symmetry, which is described by some group G, then the background gauge field is usually one form G connection, but it can also be thought of as a map from your spacetime manifold to the classifying space BG. If you specify the homotopy type of such a map, homotopy class of such a map, and that will define the topology of your G bundle over the spacetime manifold, and then the partition function of the invertible theory will depend on the topology of this G bundle. But in general, this space BG is some complicated infinite dimensional space. I'll give you some examples. If you have a U1 symmetry, then the corresponding classifying space can be taken as the infinite dimensional complex projective space. If you have a Z2 symmetry, then it can be taken as the infinite dimensional real projective space. But at this point, now a natural conceptual question arises, which is that what happens if we replace this target space BG by a more conventional space, some finite dimensional space, such as a sphere. So in this case, we'll have some map from XD to some space P, which will be more conventional than these infinite dimensional spaces. And the question is, would it be meaningful to study such invertible theories, and what are their physical significances?
So in the case of U1, you can also pick a connection on the bundle that you specify. Does the invertible field theory depend on the connection as well?
Yes, if it includes the perturbative anomalies from the boundary, then the connection is important. Yes. In this case, the extension to this arc will be important.
Thanks.
Yeah, thanks for the question. So yeah, okay. So that's the question that we want to ask. And then, of course, we are not the first ones to ask this question. This question has been asked and also answered, especially in recent years in the literature, especially by these people. So there is a natural physical context where such a generalized notion of invertible field theory becomes relevant. So here is the context. So instead of have a single trivially gapped QFT, consider having a family of trivially gapped QFTs, parameterized by some coupling constant phi valued in some parameter space P. So to study this family of trivially gapped QFTs, one thing we can do is to promote this parameter phi to a space-time-dependent background field, which can be thought of as a map from the space-time to the parameter space. And at low energy, this family of QFTs is expected to describe an invertible field theory, where now the set of background fields include this map from the space-time manifold to the parameter space. When you have such an invertible field theory, we are going to call this invertible theory a parameterized invertible field theory, since it includes some space-time dependent parameters. And in the literature, the partition function of such a parameterized invertible field theory is called the adiabatic phase. And since I said the invertible theory is completely characterized by its partition function, so for the sake of this talk, this adiabatic phase and a parameterized invertible field theory will in practice more or less mean the same thing. And then the classification of these parameterized invertible field theories remains essentially unchanged. So they still form an abelian group, and then they have the same structure. The only difference is that now this P is literally just some parameter space that parameterizes your family of trivially gapped QFTs. And as before, we have these two factors, but the interpretation is a little bit different compared to the previous ordinary invertible theory case. So let me look at this second factor first. Again, an element from this set can be thought of as a degree d+1 differential form. Again, we can think of this as an anomaly polynomial. But in this case, the relevant anomaly will be the so-called anomalies in the space of coupling constants in the sense of this paper from 2019. And in the literature, this anomaly polynomial for the anomalies in the space of coupling constants is also called a higher Berry curvature, or simply a Berry curvature. And for this first set, again, the elements in this set will be some Boltzmann invariants. And now these Boltzmann invariants match the non-perturbative anomalies in the space of coupling constants for the d-1 dimensional systems. And then the elements in this set are called them torsional Berry phase because they are a part of the Berry phase. But since this group is a torsion group, if I take some number of copies of this torsional Berry phase, then it will trivialize. And in that sense, I will call this a torsional Berry phase. And then the main point here is that so the partition function of the parameterized invertible theory, which is the higher Berry phase, can always be decomposed into two parts. One is the torsional Berry phase, and then the other is Berry curvature. In particular, this Berry curvature is simply some differential form. Okay, before we get into the most general theory of Dirac Fermions, let me first give you some simple example. So consider free Dirac Fermion in 1+1 dimensions. And this is the Lagrangian. And I'm going to couple the theory to a background gauge field for the U1 vector symmetry. And here is the mass term. And in this case, the most general mass parameter that I can write down is a complex number. And this theory is trivially kept whenever mass is non-zero, which means is that the relevant parameter space that I want to consider in this case will be a set of complex numbers minus the origin, which is homotopy equivalent to a circle. Okay, so this is my trivial family of trivially kept this. And then from our general understanding, we would expect that this family defines a parameterized invertible field theory with this parameter space. And then, as we said, this parameterized invertible theory will be simply characterized by its partition function. So what I need to do will be to compute this partition function of this Fermion theory with this mass parameter and also the background gauge field on some spacetime manifold X2. And then I'm going to divide this by the same thing with the fixed constant mass term. This is like the Pauli-Vilas regulator, so that I get some finite number.
Can I ask a question?
Sure, yes.
So the Lagrangian is not real if you take the mass to be complex, right?
It is real actually, because here, so this gamma is the chirality matrix, two-dimensional chirality matrix.
Oh.
Yeah, because of this, if you actually take the Hermitian conjugate, then you get back to the original thing. Yes.
Oh, thanks.
Okay, thanks. Are there any other questions? Okay, so we need to compute the partition function. And then we want to take the infrared limit. But since this is simply a free fermion, the IR limit just means taking the infinite mass limit. So we need to compute this quantity, and this will correspond to the partition function of the parameterized invertible theory that we are after. In this example, it's actually very simple to compute this thing, because I can simply rotate away this phase vector in the mass parameter by doing some axial rotation of my fermions. But since there is a mixed anomaly between the U1 axial symmetry and then the U1 vector symmetry, And since we are turning on the background for the U1 vector symmetry, upon this axial rotation of fermions, we are obtain this non-trivial phase vector. And because of this left-hand side will be equal to this right-hand side. And then this is the partition function for the corresponding parameterized invertible series. And in this example, since since everything is just expressed in terms of some differential forms, there is no non-trivial torsional Berry phase. And then the corresponding higher Berry curvature in this case will be some differential 3 form, since we are in 2 space-time dimensions. And then this 3 form is simply obtained by adding the exterior derivative to this thing. And the Berry curvature is given by this expression. Okay. So this system can be completely analyzed by just using the ordinary mixed tube anomaly argument. And here comes the general question that we want to address, which is what if we have arbitrary number of Dirac Fermions and arbitrary number of space-time dimensions? Even though this is simply a free fermion, it's not entirely straightforward to compute such a higher Berry phase in the most general case. So some partial results were known in the literature from these papers in particular. And then this same question has been also studied by mathematicians in recent years. So let me explain the setup in more detail. So our system of interest will be a d-dimensional Dirac Fermions given by this Lagrangian. I'm going to assume that I have nf number of labels, which can be any arbitrary integer. And this mass matrix is some nf by nf matrix, which I will denote like that. So here M0 will be some fixed real, positive real constant. This Fij will be dimensionless matrix valued function from my space-time manifold to the parameter space. So in this case, the parameter space will be a space of non-degenerate mass matrices. And then let me actually tell you how this space looks like in a little more detail. But it depends on the parity of the space-time dimension. So if D is even, then the mass matrix actually can be any invertible complex matrix. And this is homotopy equivalent to just UNF. If D is odd, then this parameter space, so that when D is odd, the mass matrix must be Hermitian. So the parameter space will be the set of non-degenerate Hermitian matrices. And this space looks like disjoint union these spaces. So these will be our parameter space of interest for free Dirac Fermions. And then the goal is the same as before. We want to compute the higher Berry phase of this system, which simply means that we want to compute such a partition function. So we have the partition function for the space-time dependent, for the Dirac Fermions with the space-time dependent mass matrix, possibly in the presence of some other background gauge field. And we have this Pauli-Vilas regulator. And then we are going to take the infinite limit. So the question is simply, how do we compute this quantity? Let me first give you a partial answer. So as we said before, so this partition function, we interpret this as the higher Berry phase for this system. And then as we said, this higher Berry phase can always be decomposed into two parts, the torsional Berry phase and then the higher Berry curvature. And then the main result of our paper is that this higher Berry curvature, which will be some degree d plus 1 differential form, can be computed by this general formula. This formula will work for any number of space-time dimensions and any number of labels. It requires some explanation. So first of all, this curly F is the field strength of something called superconnection, which I will define in a few slides. And this CH means that we need to consider the charm factor of this superconnection. And then we have the same quantity with superscript 0, and this is simply the contribution from the Pauli-Vilas regulator. And this A hat is the usual A hat genus, which is responsible for gravitational contributions. So here, this quantity is some formal polynomial of differential forms. And then what I actually need to do is to take the degree d plus 2 part of this polynomial. And then I need to integrate this differential form along a certain direction in the parameterized space. And then after that, I will obtain some degree d plus 1 differential form. And then the claim is that this differential form is precisely the higher Berry curvature that we want to compute. So in particular, in terms of the partition functions, this will mean that if our spacetime manifold XD is null-bourdant, which means that if it's a boundary of some higher dimensional manifold, then this partition function is simply computed by the right-hand side, where for this higher Berry curvature, we insert this equation. So this gives us the partial answer to our general question. So to explain this in a little more detail, I will need to give you the definition of a superconnection. So the superconnection was first introduced in the math literature by Gillen in 80s. But instead of giving you the mathematical definition, I'm going to tell you the more physicist-friendly definitions, which were given in the paper by Kanno and Sugimoto from last year. So the definition is slightly different depending on whether the space-time dimension is even or odd. I'm going to give you the definitions for the even dimensional case, but there will be similar definitions for odd dimensional case as well. So let's review that for the even space-time dimensional case. So what are the maximal set of background fields that we can consider in this problem? So first of all, the mass matrix can be any non-degenerate NF by NF complex matrix. And in addition to this mass matrix, we can couple the theory to UNF times UNF background gauge field, which I write as A plus and A minus. So in general, since this mass term will break some of these symmetries, to consistently couple to these backgrounds, I will have to let the mass parameters also properly to transform under these symmetries. Okay. So these are the set of background fields that we can consider for the free Dirac Fermions. And the superconnection, which I write as curly A, is simply a way of packaging this set of background fields into a single object. So all these things are some NF by NF matrices. And then the superconnection will simply be 2NF times 2NF matrix given by this expression. And then correspondingly, I can define the field strength for this superconnection by this familiar expression. If I just plug this definition into there, then I'll obtain such an expression. Here, one remark is that this superconnection and then the corresponding field strength, they don't have a well-defined differential form degree. For instance, here I have 1 form and here I have 0 form. But they do have a well-defined degree mode 2. So this degree mode 2 is defined in this way. So for instance, this superconnection has an odd degree, which means that on the diagonal, I'm allowed to have odd degree differential forms. And then on the off diagonal, I can only have even degree differential forms. And that defines an odd degree quantity. And this field strength has an even degree, which means that on the diagonal, I can only have even degree differential forms. And then on the off diagonal, I can only have odd degree differential forms. So for instance, you can see here that so this F plus is the field strength for this UNF background gauge field, A plus. And we have degree 2 differential form here, and then here I have a 0 form. And in total, this field strength has even degree. And this degree mode 2 behaves nicely under multiplication of these quantities. And then in the previous formula for the higher Berry curvature, we had to consider the Chern character of the superconnection. And the Chern character is defined by this expression. So this definition is very similar to the definition of the ordinary Chern character for ordinary connections. But the only difference is that instead of an ordinary trace, here I have a super trace. So super trace is defined by this equation. So here all these A, B, C, D are NF by NF matrices. And then the super trace of A, B, C, D is defined by taking trace of A minus trace of B. So this defines our Chern character. And there are similar set of definitions for the odd dimensional case. Before I go into examples, are there any questions at this point?
Yeah, I have a quick question.
Yes.
So from the superconnection point of view, why is it important that M is non-degenerate? Just from a mathematical point of view. Is there something nicer about the superconnection when M is non-degenerate?
I don't think so, but we require M to be non-degenerate just so that we have a family of trivially kept.
Yeah, I understand it from the physics point of view. I'm just curious for a mathematician, is there anything special about a superconnection when M is non-degenerate?
I see. Not that I know. The superconnection can be equally defined for any M, as far as I understand.
I see. Okay, thank you.
Then let me get into the examples. So let's revisit our previous example of two-dimensional single Dirac Fermion, which had this Lagrangian and this background gauge field for the U1 vector symmetry, and then the complex mass parameter. Previously, we said the partition function or the higher Berry curvature for this system can be obtained simply by axial rotations of fermions, and then the result was this. And I want to demonstrate for you that how this result can be reproduced by using this more general formula using the charm character of the superconnection. So here we have one flavor of Dirac Fermion. So the mass matrix is simply a number. And then since we are coupling to the background gauge field for the U1 vector symmetry, I need to set A plus equals to A minus. So if I just plug this into the definition of the superconnection, then I find this field strength, which is a 2x2 matrix. And then I simply insert this definition into this expression for the charm character. And then the relevant part of the charm character will be the degree 4 part, which is given by this. And then if we plug this into the general formula, so in this example, there will be no contribution from the Pauli Vilas regulator. And there is also no contribution from the A hat genus because the space-time dimension is too low. To compute the Berry curvature, I simply insert this expression into here. And then after doing this integral, indeed I reproduce the desired result, which is consistent with the previous analysis. Okay. And let me give you a slightly more non-trivial example, just to demonstrate how it works. So let's consider two flavors of Dirac Fermions in 3 dimensions. Since the space-time dimension is odd, the mass matrix can be any non-degenerate Hermitian matrix. And since it's Hermitian, I'm going to diagonalize this matrix. Then I will write it as U sigma U dagger. So here U is the unitary matrix parameterized by 2 angles, theta and phi. And then sigma is the diagonal matrix with real entries. So in this case, the parameter space looks something like R4 minus some 3-dimensional cones. So the point that I want to make is that the parameter space in this case looks a little bit complicated. And then computing the higher Berry curvature for this system is not as straightforward as the previous case. But our formula will still be able to compute the higher Berry curvature for us. So in addition to this mass parameter, I'm going to further couple the system for the background gauge field for the U1 vector symmetry, diagonal U1 vector symmetry. So I have 2 flavors. Then if I just plug all these things into the formula, then I obtain the Berry curvature, which is a degree 4 differential form. And it's given by this expression. So this first set of terms reflects the familiar fact that integrating out 3-dimensional mesh Dirac Fermion gives us some Chern-Simons terms, both for the background gauge field and the gravitational Chern-Simons term.
Excuse me.
Yes.
In the one flavor example, the alpha can be thought of also as a 0 form corresponding to gauge parameter of the axial gauge field. Now, in the 2 flavor case, can you, the actual symmetry could be a U2 cross U2 in even dimension. Can you think also in this case about the M's, the 0 form as a 0 form of the gauge parameters of the axial U?
Mm-hmm. Yeah, that's correct. So in this case, the most general global symmetry that I can consider will be U2 cross U2. And then this mass parameter transforms under this U2 cross U2 under the bifundamental representation. But I'm picking only the U1 vector, diagonal U1 vector subgroup of this symmetry group under which this mass parameter is actually invariant. Yeah, just so that the computation simplifies. But you are right. If I turn on the most general background gauge field, then M should transform appropriately. Okay. Yes, thank you for the question. So yeah, so I just said this first set of terms correspond to the Chern-Simons terms in 3D. And then this second term simply reflects the fact that inside of the parameter space, we have a non-trivial 2 cycle. And this second term gives us a WGW term. So this omega 2 is basically the volume form for this non-trivial 2 cycle in the parameter space. And then the point is that our formula captures all these features of this theorem. Okay, so in practice, applying this formula for many number of flavors becomes a bit tedious. But in principle, at least this is supposed to work for any number of space-time dimensions and any number of flavors. And in the remaining time, let me briefly explain how this formula is actually derived. So the main idea here is to realize our d-dimensional Fermion theory of interest on an interface of an auxiliary d+1 dimensional free Fermion system. So from now on, let me assume that the space-time dimension D is odd. When D is even, I can do similar computations, but some technical details will change. So this was my d-dimensional Lagrangian for the d-dimensional Fermions of interest. And then this d-dimensional system lives on the space-time manifold X, which is a closed d-dimensional manifold. And then I'm going to consider an auxiliary d+1 dimensional system given by this Lagrangian. So it has some mass parameters. In particular, this mass matrix will be equal to the original d-dimensional mass matrix. And then I'll have this additional mass parameter. I'm going to put this d+1 dimensional theory on a particularly designed d+1 dimensional manifold Y. So this Y is a closed manifold, and it looks like this. So in the middle, it just looks like the product of the d-dimensional space-time manifold X times an interval. And then to the left and then to the right, I'm going to close this manifold by this Y plus and Y minus. And inside this Y plus and Y minus, all my background fields, the mass parameters, and then also the background gauge field should appropriately be extended into this arc. And the important thing is that I will let this mass parameter, additional d+1 dimensional mass parameter M1 to vary inside this middle region in this way. So I will make an interface using this M1. And an important thing is that except for this M1, all the other background fields, gauge field, mass parameters, Mij, and also geometry, everything is left-to-right symmetry. And then the point is that if I make such an interface, then the original d-dimensional system of interest will appear as the localized modes on the interface. So there will appear exponentially localized modes. These modes correspond to the d-dimensional system. This you can check simply by solving the d+1 dimensional Dirac equation for this system. Okay, and with this setup, I want to first argue that the partition function, the regularized partition function, this d+1 dimensional system on this manifold Y, in the limit where this interface becomes infinitely steep, actually simply coincide with the d-dimensional partition function that we were interested in. Here for the d+1 dimensional regulator, this superscript 0 means that I still take the same interface configuration for this M on Y, but I'm letting the d-dimensional matrix to be a constant. Okay. And intuitively, this equality can be understood as follows. So this d+1 dimensional partition function has contributions from localized modes, which is nothing but the d-dimensional partition function of our original theory. And there will be additional contributions from the delocalized bulk modes. But the point is that as we take the limit where this interface becomes infinitely steep, these contributions from the bulk modes will cancel out in the numerator and then denominator when we compute such a ratio. This is simply because if we look at the d+1 dimensional Lagrangian, in this limit, only this middle term will dominate in the action. And then this middle term is the same in the numerator and then the denominator. So if we compute this ratio, then this contribution simply cancel out. And then as we claim, this d+1 dimensional partition function in this limit will simply reduce to this d-dimensional partition function. Okay. So this is the first step to derive the formula for the higher Bay curvature. And then next, as we related our d-dimensional partition function to this d+1 dimensional partition function, now we can actually compute the phase of this d+1 dimensional partition function by the so-called folding tree. So remember that our d+1 dimensional manifold Y looked something like this, where there was an interface in the middle. And then on the right, we had like plus M0. On the left, we had minus M0. Then we are taking the limit where the interface becomes infinitely steep. And then what we can do in this setup is that now since the, except for this, the value of this plus minus M0, since the manifold is symmetry, I can cut this manifold along the middle, and then I can fold this left part back to this right part. So if I do this, then what this tells me is that the phase of this d+1 dimensional partition function is actually equal to this ratio of determinants, where this k is d+1 dimensional Hermitian operator given by this expression. So this k depends on my d-dimensional mass matrix and also the background gauge field. And this expression simply defines what is known as the exponentiated eta invariant for this Hermitian operator k. So this eta invariant is defined by a formal sum over all the eigenvalues, real eigenvalues of this operator K. And we need to sum over the sign of these real eigenvalues. And then it should be properly regularized. And if we combine this observation with the previous result, that saying that the d plus one-dimensional partition function is simply equal to d-dimensional partition function in this limit, then I arrive at this conclusion that the phase of the d-dimensional partition function is actually given by this exponentiated eta invariant.
Sorry, quick question. Can you comment on the boundary condition you get after the folding?
Yes. So yeah, actually, yeah, I was being a little bit sloppy here. So after folding, I'm going to have a manifold that looks like this. And then, so here I said this operator K is Hermitian. Actually, since now I have a boundary to make, so in general, so the hermiticity of this operator will depend on the boundary condition that I impose here. So to maintain the hermiticity, I will have to impose some non-local boundary condition, which is called the APS boundary condition for this operator K. And only then this operator will be Hermitian, and then this sign of the eigenvalues will make sense.
But presumably the boundary condition is not up to you, right? Shouldn't the folding trick dictate a particular boundary? Okay, just
exactly. So yeah, I was only sketching the derivation, but to do this very precisely, I can follow the tricks that are introduced in the paper by Yonekura and Witten and Yonekura a few years ago. And if I do it very precisely, then I'll be forced to have the APS boundary condition here. Yes.
I see.
Yeah, so precisely speaking, this eta invariant is the eta invariant of this operator K on this manifold with the APS boundary condition imposed. Yes. And this equation is true only with those assumptions. Yes. Yeah, thank you for the question. So, okay, so this was where we were. And now, since we related our partition function to this exponentiated eta invariant, we can try to use the APS index theorem, which relates this eta invariant to some other quantities. So the statement of the APS index theorem is as follows. So I have some d plus two-dimensional manifold W. And then the index theorem tells me that this eta invariant computed on the boundary of this manifold is equal to this right-hand side. And this index of this operator Q is some integer. So it's not going to play any role for our purposes, because in the end, we are going to exponentiate everything, and this integer will simply disappear. And then I have this remaining integral. And then here, so the question is, so in this equation, now we want to take the limit where the d-dimensional matrix becomes infinitely large. In this limit, this absolute value will just become 1. And then furthermore, if we assume that our x is null burdened, then we expect that this quantity in this limit to become the Berry phase, exponentiated Berry phase, integrated over this null-Bordism y. And then the question is now to compute this right-hand side in the same setup using this APS index theorem. And this is a little bit technical, so I'm not going to explain all the details, but just to give you some flavor. So this is the actual D plus two-dimensional manifold that I need to consider to achieve such a board. In particular, this will be some non-compact manifold which looks like a cylinder. But the claim is that if I apply this APS index theorem to a particularly chosen D plus two-dimensional manifold, then I can actually derive from this that this very curvature is actually equal to this general formula that I claimed before. And that's how we derive this higher Bay curvature in general. Okay, so let's rewind a little bit where we are so far. So I said the higher Bay phase can in general be decomposed into two parts, the torsional Bay phase and then the higher Bay curvature. And then at this point, I'll say that at least for free Dirac Fermions, this higher Bay curvature part is completely understood because we simply have the closed form formula for the higher Bay curvature that works for any theory of free Dirac Fermions. But still there remains the question. So this torsional Bay phase part is not as well understood. So in the remaining 2 minutes, I will just show you that there exists an example of a torsional Bay phase that comes from a free Dirac Fermion, and then I will end there. Okay, so this is the I think the simplest example of a torsional Bay phase that comes from free Dirac Fermion. So again, I consider a single Dirac Fermion in 2 dimensions. So I have the complex mass parameter as before, but this time I'm not going to couple the system to any other background gauge field for the internal symmetries. So this will be my Lagrangian. And then if we use our formula, then I can see that the Bay curvature in this case simply vanishes. Then from our general understanding, we can expect that the partition function of this theory in the infinite mass limit will define some Boltzmann invariant valued in this set. So I have this S1 parameter space here, and then I have spin structure because I have fermions. And this group turns out to be isomorphic to 2 copies of G2. And one of these G2 factors correspond to the usual alpha invariant. And this alpha invariant is a purely gravitational invertible theory. So this doesn't see the parameter space. So in this context, we will not be interested in this G2. But this another G2 factor tells us that there is a possible torsional Bay phase with this setup. And the question is whether this theory defines a non-trivial element in this G2 or a trivial element. And this question can be answered by simply evaluating the partition function of this theory on the generator of this Boltzmann group. And in this case, the generator of this Boltzmann group, omega2 of spin S1, the relevant generator is this guy. So I have a torus, and along one cycle, I'm going to impose the anti-periodic spin structure, and then I will let the mass parameter to wind around this cycle. And along the other cycle, I'm going to impose the periodic periodic spin structure for the fermion, and then I will let the mass term to be constant along this direction. And then we can actually compute the partition function of our 2-dimensional theory on this torus in the infinite mass limit. This can be done either just explicitly by explicitly solving the derived equations, or it can also be done actually using our previous formula. But the upshot is that the result gives us -1. So this defines a non-trivial element of this G2 that we had before. The conclusion is that this theory actually defines a non-trivial parameterized invertible theory with a vanishing by curvature. So this will be a very simple example of a torsional Berry phase. Okay. So with that, let me summarize. So I told you about parameterized invertible field theories, in particular the ones that come from the low energy limit of free Dirac Fermions with spacetime-dependent mass parameters. So I told you that any higher Berry phase can be decomposed into the torsional Berry phase and then the higher Berry curvature. And then this higher Berry curvature for any theory of free Dirac Fermions can be computed by using this universal formula, which is given by the charm character of the superconnection. And there are some obvious future directions. It'd be great if we had some better understanding about this torsional Berry phase, and it's in the example of free Dirac Fermions. And then one final comment that I want to make is that although I put all these stories into the context of this parameterized invertible field theory, in the end, the question that we are actually answering is an extremely basic one, I think. So I'm just asking how to integrate out infinitely heavy Dirac Fermions in the presence of some background gauge field and then some background Higgs fields. So these mass parameters, I can think of them as background Higgs field. And then this answer that I'm giving here is just telling us that what are the topological terms in the effective action that I get after integrating out such heavy fermions. So I think this is an extremely basic question, and then I'll be really happy if this formula finds some broad application. Okay, with that, I will end my talk. Thank you very much for your attention.
Thanks, Yichul, for such a nice talk.
Thank you.
Are there any questions? Okay, let me turn off the recording.